So we on? Okay, so I've been asked to talk to the American Welding Society about the evolution of the American Welding Society, and I decided to talk about the past, the present, the future. But to begin, I want to talk about why joining is important. And so it turns out I'm at MIT, and this is MIT today. This is just about exactly 100 years ago. We're sitting over here in this little building over here. MIT moved across the river into Cambridge from Boston 100 years ago last month. So it turns out if we look at welding, welding is a foundation to all the manufacturing that we do, all the products, whether it's micro components or huge ships or other things. It's important to our security, and it's also important to our comfort. If we look at needs of different people, well, before I do that, this is the outline of what I'm going to go through. I often use the U.S. Army's approach when they're teaching new recruits. First you tell them what you're going to tell them, then you tell them, and then at the end you tell them what you told them. Because they hear it 3 times, and then maybe they'll learn it the 3rd time. Anyway, joining is fundamental. It's an integrative process that's multidisciplinary, uses lots of different engineering fields of study. It's improved the size and reduced the cost and improved the reliability of virtually everything we build. It's found everywhere. It's ubiquitous, okay? It's a very large fraction of the manufactured cost, which is one of the reasons it's important to our manufactured product. It's important to the quality of what we build. Many of the failures are related to the joints. It's often and almost always has first been applied as an art before we ever understood the science behind it. The science tends to follow the art in welding because of the great need to be able to join things. There are relatively few people in this country that are educated in welding. We probably turn out 50 welding engineers a year in this country. In the Soviet Union, or former Soviet Union, they turn out about 5,000, okay? And you can actually see the difference in the way they do things in different countries because of the difference in the number of people who actually educated in welding. And the ability to join something, particularly new advanced materials, often limits the use of materials. Now, one of the reasons we're doing things in general is because we're trying to fulfill some need, and it turns out the guy Maslow came up with a list of needs, a hierarchy of needs a number of years ago, and joining is important because it fulfills some of our needs. So there are basic needs, which are the psychological needs of food, shelter, clothing, and safety, and then your psychological needs of esteem and love and belonging. And then there's the self-fulfillment needs where you actually can start worrying about the environment and all kinds of other things. I remember once we had the World Economic Forum here at MIT, and I was chairing a session on the environment. And I had someone there who was Minister for the Environment, this is like 1992 or so, Minister of the Environment for the former Soviet Union. And someone asked him a question. We had a little panel discussion, and someone asked him a question and says, "Why don't you do things more environmentally friendly?" They had the the Siberian pipeline, and it was leaking oil all over Siberia. I mean, it was just full of leaks. But they kept on pumping oil from Siberia, and he said his answer was, well, back in 1985 when we had perestroika and detente, this was under Gorbachev, he says everybody, as we were regaining our freedom, people were very interested in the environment. But today, which was 7 years later, we're just interested in eating, okay? And they were going to sell oil. And then we had someone, Amshad Irani, who was head of Tata Steel in India. And someone said, well, why don't you make steel in India in a more environmentally acceptable way? And he says, well, we would like to make steel in a clean way, but we don't have the technology and we can't afford to buy your technology to do it. If you'll give it to us, we would be happy to use it. But in fact, India sits on $5 a ton iron ore, and we're going to sell it because we need the international exchange. So we have an advantage, inexpensive iron ore, and we're going to sell steel. We're going to make steel. We don't want to make it dirty. We're going to make it in any case, and if you'll give us the technology to make it clean, we'd be happy to use it. But we need the foreign exchange. So if you start looking at people's needs, they have to, you're at different levels, okay? In some parts of the world, they're just interested in food, shelter, and clothing. In other areas, we can worry about doing all kinds of inefficient, expensive things because we're more interested in some other thing because we can afford to be that way, okay? We can't always afford those things. But it turns out in recent years, people have found something that comes even before food, shelter, and clothing in our needs. And here it is, Wi-Fi and batteries. It's more important to have your connection to the internet. Pardon me?
Mostly batteries.
Mostly batteries?
Like a 3-week iPhone?
A 3-week iPhone would be wonderful, yes. I mean, except I don't know if you're going to actually fast for 3 weeks before while you're on that iPhone. But anyway, you're right. I mean, but these are basic needs. And we found new needs as time goes on. Joining has increased the size of what we build. So here's an old bridge. I think it's in England somewhere, an old stone bridge. And you could go across small bodies of water. But today we have huge bridges. And it'd be hard to imagine how we would build something of that size without modern joining technology. And what I really should have done is put together a picture of a pressure vessel. If you think of pressure vessels that now are 4 inches thick, can you imagine riveting a pressure vessel like that? 4 inches thick with rivets? It would be nothing but overlaps, right? So because we have welding, we can make things that 100 years ago we couldn't make. It's decreased the cost of things, and so I'm using here a computer. Here's one of the old computers versus a new computer. What's going on there? Well, that's interesting. PowerPoint, Bill Gates knows what I want to do, I guess. Anyway, okay, so it's also improved the reliability and life of products. There's one of the early kind of 1950s helicopters, Bell helicopter. And it's basically a very simple design, very light. It carries about 1 person and not much more, okay? Actually, during the Korean War, it would carry 2 people. They actually would have a stretcher hanging off the side. And you may have seen that in MASH or something. Here's a modern Eurocopter that goes at like 230 miles an hour. And of course, we have the V-22 Osprey, which can go at 300 miles an hour when you tilt the rotors forward. Does anybody know why helicopters are limited in speed? Yes?
Because the Mach drag caused by the advancement of the blade.
Exactly. It turns out you don't want to go supersonic because you get all kinds of forces that rip things apart and stuff. And it turns out the advancing blade, the tip, is actually getting to the sonic velocity, okay? And that limits your speed. If you go down to Hampton, Virginia, and you go over to the NASA site, they have a picture of a helicopter that they put a jet engine on, a rocket engine basically, and they forced it to go, with the tip speed going around. It was would have to go supersonic, just to try it out. And some pilot who didn't really care about whether you lived or died flew it. Okay, but was it jet pilot? Probably yes. I mean, well, those guys didn't care anyway. Joining is also complex. I mean, this is actually the V-22 Osprey engine and drive shaft. But anyway, it's pretty complex. I remember the first time I ever saw a V-22 Osprey, and I looked under the nacelle to see the engine. I said, wow, I've never seen anything that complex except the inside of a nuclear sub. Okay, in terms of everything going in every direction and crisscrossing and stuff. And this doesn't even give it, I mean, if you actually put it inside the nacelle with all the other things, this doesn't even make it as complex as it really is. And here's just an oil refinery, a chemical plant, showing the complexity and all the joints that go in that. So joining is everywhere, from small microwave circuits. This is Noyce in 1961, one of the first integrated circuits. Pretty simple. To, I say, from chips to ships. Nice cruise liner here. Joining is everywhere we go. It's fundamental to our manufacturing. Okay, it's foundational to what we do. Oops. In terms of manufacturing, I often, for many years, have asked students and others to think of the largest standalone object that does not contain a joint. So anybody have an idea? I mean, people would say a nail or a needle. That's not very large, okay? So anybody have, I've gotten milk cartons, but even a milk carton's got to have a top, right?
Maybe length of asphalt road.
Length of asphalt road, except that's the asphalt road is actually a composite, so it's full of joints, right? In the sense of you got your aggregate and you got your asphalt, and so you got to have those things sticking together, right? In that sense, yes. Ship propeller. If it's cast, yes, that's actually pretty good. That's huh? Oh, an uncle?
Anchor.
Anchor. Oh, an anchor. Yeah. An anchor, yep. Although to make the whole thing functional, you got to have it connected to a chain and things. But okay. But so I gave this challenge once to some faculty, and one of them came up with an anvil. But your ship propeller is pretty good in terms of a standalone object. I'd say it beats the anvil in many ways. That was Frank McClintock, who's retired now, but was a faculty member of mechanical engineering. I mentioned this once to a bunch of faculty, and Frank fretted about this for like 3 days. You know, what was the largest? Well, it turns out the largest, depends on how you define it, but I call a standalone object. The largest manufactured object that I can think of is a generator rotor forging, and it weighs about 700 tons. The forging's going to be machined down into a big long thing that's going to generate 1,000 megawatts electric power. There's a man right there, okay? Man standing there. So this is a lot taller than a man. It's about 10 or 12 feet tall and weighs 700 tons. But it's really just a big paperweight, unless it's sort of like, you know, your anchor was a good one, okay? But it's standalone. I mean, the anvil was pretty good in the sense that you don't really need anything else to go with it, okay? And I think, what was yours? The propeller. The propeller's pretty good. I actually came up with the largest in weight that I know of is an ingot mold for the generator rotor. Okay, it weighs almost the same amount as the generator rotor itself. Okay. By the way, when I was a young engineer at Bethlehem Steel 40 years ago, I was given the job of trying to weld two big forgings together because there was limited capacity in the world to make these great big generator rotor forgings. They'd like to make them even bigger than if they could, but at the time they were estimating it would cost $1 billion to build a new facility to cast, heat treat, forge, machine these rotor forgings. And it turns out Bethlehem Steel could turn out one a month, and U.S. Steel had a facility and they could turn out one a month. So we had the capacity to make 24 of these in the United States, and I think the French had a plant that they could make another one. But you could only make so many, and people were projecting, this is the mid-70s, the electricity usage was going to outstrip all this, and so we were going to have to figure out how do we get more generator rotor forgings because we don't want to invest $1 billion in a new production facility. And so I was asked, how do you weld something that's about, you know, has a cross section about 6 feet by 6 feet, okay? Two big long objects that have a cross section of about 36 square feet or so. Well, obviously I wasn't going to be able to do a whole lot of test welds because they get kind of pricey at that size. But in any case, where was I going with that? Oh, I was going to tell you, why did we have those two facilities at U.S. Steel and Bethlehem Steel? Because of the Navy had them built because of the battleships back at the turn of the 20th century. Okay. for all of
Tops or guns?
the guns, the battleship, you know, the barrels, okay?
There's a lot of Fritos at regular shipyard sitting in the grass.
Yeah, I would, big long furnaces, they're straight down. You'd lower that barrel right straight down in a vertical furnace that's about 40 feet long or whatever. If you start thinking about some of the sizes we used to build, and we couldn't, in those cases, they weren't doing it by welding because welding wasn't a sophisticated enough technology. So anyway, an ingot mold's the largest thing I've come up with. Joining occurs at the end of the manufacturing process where the cost of repair is high. And joining also is a relatively large fraction of our manufactured cost. Typically, joining could be 10 to 20% of the cost of a manufactured product. And people say, well, that's only 10 or 20%. The material cost is usually much less than 10%, okay? So joining is actually a larger fraction than the actual cost of the material in most cases. The inspection cost is about similar to the joining cost. And if you take my course on material selection, I actually go through some of these things. It's actually in the handout you have on the 21st century research needs. It breaks it down, what the fractions of manufactured cost are typically for something. Okay, so joining occurs at the end of the manufacturing process. We're talking about a big pipeline. We've already made the pipe. We've dug the hole. We've put it in there. Someone's welded it. Someone comes along and inspects it. And if it doesn't pass inspection, your whole project is delayed, and you're talking about $1 million a day delay time or something. If you're looking at some printed circuit board with solder joints, one bad solder joint out of 10,000 joints can destroy the whole project. And you got to go in there and fix it individually. And so rework is often a problem. Now, it's actually easier to do it right the first time. And I have two kind of examples I've run across in my career of learning to do it right the first time. You've all seen people who have pagers, okay? So that someone is, you know, nowadays we all have cell phones, but before that, a lot of people carried around a pager. Doctors still do to a certain extent, but now the cell phones almost are like pagers. But back 25 or 30 years ago, pagers were one-of-a-kind type of products because they had to have a separate frequency for each pager. And Motorola had moved the manufacturer to Singapore. And if you went into a Motorola store and ordered a pager, it would take 6 weeks to receive the pager, okay? And Motorola decided, well, we could move the manufacturing back to Boynton Beach, Florida, where we can get a lot more vacation time by going down to Florida to visit the plant. Anyway, they moved it back to the United States because this was 25 years ago. They moved it back to Boynton Beach because they could get the delay time from 6 weeks down to about 3 or 4 days. From the time you ordered it, you'd be able to come pick it up 3 or 4 days later. Nowadays, you get things instantly, but people were trying to shorten the manufacturing time. But the manager who was setting up that plant to manufacture these things, it was going to be very automated. Almost no people. It was going to be lots of robots putting this together and things. They said, well, they showed him the layout of the factory, and they had a rework area, and he says, no, get rid of that. We're not going to have a rework area. Well, the rule of thumb in the electronics business was you had to do 6% rework. That was what everyone had found for years. When you're building printed circuit boards, you had to have 6% of your product had to be reworked. And he said, no. And they said, no, what are we going to do? He says, if it doesn't work the first time, we're going to throw it out. Well, you can't afford to do that. He says, no rework area. Well, he was the boss, and that's the way they built it. And it turns out the manufacturing engineers, when they had a problem, found that they had to go solve the problem. They couldn't just send it to rework to get fixed. And it turns out all of a sudden that Boynton Beach factory had 0 rework. Okay? Another example of the same thing, I was visiting a Ford plant where they made Mustangs back in the 1990s. And it turns out they assemble the car and they'd fill it with gas at the end of the assembly line. A guy would supposed to drive it away, get in, turn the key, and if it started, he'd drive it out to the parking lot, and then they'd go to the railroad cars and ship it off to wherever it was going to be sold. And if it didn't start at the end of the assembly line, they'd bring up a big tow motor and they'd tow it out to the rework area to figure out why the thing wouldn't start. New plant manager comes in and says, no more tow motors. If it doesn't start, you push. You know, within weeks, every one of them was starting first time. Okay? So a lot of your quality and your rework has to do with what you're willing to accept. Okay? And what you're going to fix, because everyone's busy. You've been in shipyards and manufacture. You got plenty to do, but you prioritize what's important. And if sometimes the important thing is you don't want to keep pushing these vehicles out there into the yard. There was one other example that I can't think of right now. But anyway, so quality should be built in if you can, but in any case, joining is fundamental to the quality of our manufactured products. And in fact, the quality of the overall product, whether it's a glove box, this is a glove box for reprocessing plutonium, okay, nice welds, okay, or a printed circuit board, the quality has to be uniform and good as far as that goes. Now, when I first started teaching here 40 years ago and had kind of selected joining as one of my areas, we had a faculty member here. He passed away recently, but he was teaching fracture, and I heard from some of my students that in his fracture class, he would say that something won't fail unless it's been welded. And that was Professor Reggie Pelou. And he was from France, and he came here and did a PhD in this department, went off to Boeing and doing fracture, and then came back here as a faculty member. And when I heard that from my students, I thought, oh, and then I thought, within a second or two, I said, well, no, that's actually good. As long as I keep failing, I got a job. Okay? And I have had a job for the last 40 years because joints fail. But I want to talk about why they fail. But so this kind of became a fairly common phrase around here about something won't fail unless it's been welded. And Professor Russell said, or cast. Castings also fail. There's a bunch of porosity in this casting, and here's a casting that cracked. Castings and welds, some cases for similar reasons, are likely to fail. I remember when the Space Shuttle Challenger blew up, some of my students, I went into the student's office for something, they said, did you hear? The Space Shuttle just blew up, okay? And I said, I bet it failed at a joint. I think I said, I bet it failed at a weld, okay? And I've been here for about 10 years at the time. I was wrong. It didn't fail at a weld. It failed at a joint, an O-ring joint. And the reason things fail at the joints is because they're usually the most highly stressed locations, okay? We tend to put them at the corners, okay, or at the intersections. It's not that the welds are inherently bad. In fact, in steel, the welds are actually some of the strongest material. We've actually tried in some cases to make structures completely out of weld metal because the weld metal actually has better properties. We can get better properties in the weld than we can in the bulk of the material because each weld is a small little casting, and that small little casting can have better properties than the great big casting that they make the plate from. So welds actually have progressed in quality quite a ways, but there's still a lot to be said. We tend to use larger safety factors. You look at the structural welding code for bridges and buildings, the safety factor on static stress is 1.67, 5/3. For welds, it's double that, okay? We assume there are going to be defects. It's done manually. It's done by people who had a bad night or as we know in some cases, are on drugs or whatever, okay? In fact, any of you spend time in an electric boat? Okay? So you ever looked at the, there's a, Used to be a parking lot, parking garage right across from the main gate, right? So what's that look like at lunchtime? Sleeping in the cars. Well, I used to see an awful lot of, well, they weren't sleeping in the cars, they had a lot of motorcycles. And it looked like a hippie convention, okay? But these are the guys that were building the ships another half hour later and a half hour before, right? And you kind of look there and say, oh, okay. They didn't look like your number one technicians. And they actually did a very good job, okay? But they had to have a lot of supervision, right? Yes. So anyway, so there are some problems. Okay, jointing's fundamental to our productivity. We can build things faster, cheaper, more reliably. Productivity is important because as MIT back in the mid-'80s, we had a dean of engineering who was very concerned. The Japanese were eating our lunch in the marketplace with Toyotas and General Motors making junk, and Ford was making more junk, and Chrysler was doubling that. And the opening sentence of that book was, "To live well, a nation must produce well." And the book was called Made in America. I actually participated in one of the study groups about steel in that. Paul Krugman, who had been an economics professor here at MIT, then he went to Stanford, then he went to, I think he's at Columbia, or now he might be at Princeton. But anyway, he's hopped around, but he did win the Nobel Prize, and he used to say, productivity isn't everything, but in the long run, it's nearly everything. And I'll show you some of the data about productivity. Real-world manufacturing output per worker, okay, in the United States, and this comes from the Bureau of Labor Statistics and Bureau of Economic Analysis. So these are official government figures, and you can then, that tells you what level of credibility you want to give them, right? But anyway, actually I got a good story on that. But anyway, real manufacturing output from 47 to 2010 per worker basically is, now it's about $140,000, okay? I remember back in the mid-'90s when it was around $100,000, I had a student working at Boeing, and he was working in the door product center. Now this was a very interesting manufacturing operation where they build the doors to the, you know, you walk through the door to get on there, Boeing 737 or 747, they build that door. And it's an interesting process because it might take 3 years back then to build the aircraft. You get the order, you lay the keel. They call them ships because they actually have keel beams. And then they build the fuselage around that keel beam, great big aluminum I-beam basically at the bottom of the ship. Anyway, and it only takes about a year to build the door. And so it was deterministic. You knew exactly how much product you had to produce because they started the ship that it's going to go into 3 years before, and you had I only had a 1 year lead time. And so you know exactly how many doors you had to produce. And they had, I was asking questions about it, and they had 250 employees. I said, how many doors do you build each year? 750. I said, what's the door cost? And they said, oh, we don't know, because it was all internal kind of transfer within Boeing, right? They didn't sell them outside of Boeing. The guy says, I don't know. I said, well, I think I know. If you got 250 people making 750 doors, that means each person should be producing at least about 100 in the aerospace industry. I gave them a little more credit for being a little more productive at $150,000 per person. And so if you got each person produces about 3 doors, they've got to be $50,000 doors. Now, some of those doors are the escape hatches, you know, down halfway down the, you know, when you jump out the aisle, when the ship, when they land and you have to have an emergency exit. And some of them are great big freight doors, but on average, when you walk through that door, now this is like $1995, that's a $50,000 door, okay? And if you saw the complexity, it takes like 5 drill holes of someone sitting there with a little air gun. First you gotta drill the hole subsize, then you gotta ream it full size, and then, I don't remember all the things, but I remember watching it. Every rivet had like 5 different holes drills going through that hole before they actually completed that rivet. Anyway, the manufacturing output in the United States is now about $150,000 per person per year, and that is the highest in the world, okay? We are the most productive country in the world, and we were back in 1985 when we were having our lunch eaten by the Japanese. Does anybody know why, if we were the most productive, why we were losing in the balance of trade and everything else? Pardon me? Quality? No. Well, quality was why we were not making all of it, but productivity is not the same thing as competitiveness. Okay? I've got a story about that too. But productivity is how much a worker can produce. Okay? And if you took one of my courses, actually maybe I cover it in one of the welding modules when I talk about steels. But for example, if you go back, how many years ago? 350 years ago, when they started Saugus Iron Works. Saugus Iron Works was the first ironworks in the United States. It's right up here in Saugus, Massachusetts. You're looking for a free trip to see something you can see. It's a national historical park. You can see the first ironworks, okay, in the United States. And there's an interesting story behind that about why they started building ironworks and glassworks in North America. Turns out they had an energy crisis. They're running out of firewood in England, literally, okay? So that's part of one of the other lectures. But in any case, so they had lots of forests over here, so they built an ironworks over here in Saugus. And I've estimated it was probably about 4,000 to 6,000 person hours per ton of iron produced. Because you had to cut the trees, you had to turn it into charcoal, you had to dig the ore. You start all doing that and you just didn't produce that much. Anybody have any idea of how many person hours per ton of steel it is today? Less than 0.03, yes. 0.03 was the number about 5 years ago, but it continues to improve. Less than a half an hour, less than 20 minutes, okay, per ton. So that's a pretty good increase in productivity over the years, okay? And so we're always trying to improve productivity. Oh, actually, the other story on that, since I'm just killing some time here, is with stories, and you don't have to be out by 9, right? So I was serving on a committee down at the National Institute of Standards and Technology in Gaithersburg, Maryland. And this was their manufacturing group, and I was on a review panel to review them. And the first guy gets up and he says, well, we are the nation's, the Department of Commerce, we are the nation's competitiveness laboratory. And as he was talking, he got to questions at the end. I said, well, you said you're the competitiveness laboratory. Didn't you really mean you're the productivity laboratory? Oh, no, we're the competitiveness laboratory. I said, well, do you understand the difference? Oh, yes, we're the competitiveness laboratory. I said, so you affect the exchange rates? You affect the environmental laws? Oh, no, we don't have anything to do with that. Well, that's what competitiveness is, okay? Competitiveness involves all these other factors. Productivity is how efficiently you manufacture something, but what the price you sell it at depends on what the exchange rate is. And for instance, right now, everybody thinks China is a great manufacturing country, okay? Well, they're not as productive per person as we are. And there is something in economics called the law of comparative advantage, but which I won't get into right now. But we are more efficient in manufacturing things than the Chinese, but they artificially keep the exchange rate in their favor. Now, the Japanese did this back in the 1980s. When I lived in Tokyo for a year with the U.S. Office of Naval Research, it was 240 yen to the dollar. Today, it's 100 yen to the dollar. Anybody live in Japan in the last year or two? It's around 100 yen to the dollar, right? 120 yen to the dollar. So at 120, it's half the number of yen to the dollar, which means Ichiman, instead of when I was there, Ichiman was a $40 bill, and now it's an $80 bill, right? okay? Ichiman is the 10,000 yen note, okay? But in any case, the Japanese, when Ronald Reagan decided to build Star Wars and bankrupt the former Soviet Union, and that's how we actually beat the former Soviet Union, we bankrupted them, okay? We didn't have to go to war, we just financially wore them out. Did a fair amount of wear on us too, but nonetheless, the Japanese were loaning us the money to go into debt so that we would buy their Toyotas. And we had an exchange rate then of 240 yen to the dollar. And today we're paying them back at 120 yen to the dollar. So we're just taking a 50% discount on that loan. And the country in the world that has the currency where oil and energy is bartered and sold has this advantage. Oil, gold, and things are sold in dollars. And so we are the benchmark. And what's going to happen with the Chinese as they continue to resist letting their money float, we're going to end up paying them back at 20 cents on the dollar. They now hold about $2 trillion of U.S. debt, okay? And when they finally can't stop all this, they're going to have $2 trillion in U.S. dollars, and they're going to find you can't eat dollars. Remember the hierarchy of needs? Food, shelter, and clothing? Well, dollars might be fun to have in the bank, but when it comes to starving, you can't eat them. Well, you can, but they don't taste that good. So we have this significant advantage as long as we can keep finding countries that will loan us money and not let their exchange rates float. And so that's the economics lesson for today. Anyway, food, clothing, and household furnishings, we went from 40% in 1950 to 13.5% for the basic needs cost in the United States. We have lots of extra discretionary income, although none of us feel it. Okay? You can't go to Disney World. Well, you couldn't go to Disney World in 1950 either. It didn't exist. Okay, manufacturing output versus employment. You can see that manufacturing employment has taken a big nosedive. About this time right here, I testified before Congress about manufacturing jobs and productivity in the United States, and I was basically predicting. Now, this is a scale that doesn't go to zero, but it's dropped by a third, okay, in just the last 10 or 12 years. So employment is going down. And if you hear my story on steel in the 1980s, everybody was maligning the steel industry, but it was actually because productivity was going up in the steel industry. In the decade of the 1980s, the productivity in the steel industry in the United States doubled, but our consumption stayed the same. So guess what happened to employment? Went from 500,000 employees to 250,000 employees in the steel industry. And Wall Street says, oh, steel is dead. I don't think it's quite dead. And if you take I will talk about that in some other lectures. But anyway, so if we keep going, joining is often applied as an art before the science is known. Pressure welding, which is like forging, okay, forge welding. Pressure welding is a type of mechanical energy. Electric arcs are electrical energy. Resistance, which actually became before arc welding, is electrical. Oxy-fuel is chemical energy. Thermite welding, which we'll talk about later in the course, is chemical form. Electron beams, they were we had them in the 1930s, but before we started doing anything practical with them in the 1950s, one of the first things we were doing, aside from melting metals, we were welding them. Laser, within the first year or two of inventing the laser, they were using them to repair vacuum tubes, okay, by welding them and stuff. Particle beams, okay. I was involved in 1992. Peace was breaking out with the former Soviet Union under the Star Wars initiative with Reagan. The naval warfare, well, they don't call it the Naval Warfare Center anymore, but it was basically White Oak, Maryland. What do they call it now? The Naval something. The warfare sounds too aggressive nowadays. But anyway. No, not Carter Rock. This is White Oak. Anyway, this is Carter Rock's the NAVC lab. White Oak is someone else's lab, another part of the Navy. I can't remember. But anyway, they had spent $250 million on developing particle beam weapons. And the idea, because they started this not too many years after the British cruiser, the Sheffield, got hit by an Exocet missile in the Falkland Islands War. And they lost the Sheffield, the whole, major capital ship, because of one Exocet missile and stuff. And so the Navy was concerned about, small missiles coming in and wiping out a ship. Now, the whole story about why the Sheffield, actually the superstructure caught fire, and then there's debates about why that was, but the Exocet certainly ignited it. Anyway, they decided they're going to develop particle beam weapons. Now you have the Phalanx system, which just shoots a bunch of bullets out there, right? But they wanted something that they could aim this thing, and from 30 miles away they could shoot a particle beam weapon and shoot down the incoming missile, right? Well, they spent all this money, and some of these machines went up to 45 million volts, which would be sort of interesting because you'd have to clear the ship out from all the X-rays that Anyway, but anyway, they were doing the research on this, and turns out in the end they couldn't quite get 30 miles. They could get 30 inches, okay, for the beam in the air. But that's another story. In any case, they had a 3-day workshop, and they called me down to give a presentation. They wanted to know if you could weld a submarine together, because they were trying to find peaceful uses. I'm not sure welding nuclear submarines is a peaceful use, but nonetheless. And I said, when they told me about it and all the power these things had, I said, well, you might be able to melt a submarine, but you don't need more than 10 kilowatts to weld. Anyway, so when they first started developing particle beams, one of the things they were looking at was trying to weld with them. So as soon as a new form of energy comes along, we tend to use it to try to weld. Okay. There are relatively few people trained in welding. I mean, here's a welding school from an old picture. Today, I mentioned in the United States, we don't educate that many graduate 4-year engineering degrees. There are 4 schools. The big one's Ohio State. People are familiar with welding engineers coming out of the welding engineering department. Le Tourneau down in southern Louisiana, Texas, actually in Texas, I think. Ferris State of Michigan and BYU, Idaho are the only schools that I could find that have 4-year welding engineer programs.
For example, Shipyard, the welding engineer code, their entire office is painted silver and red. And it's all Ohio State grants.
Right.
Guy from or something there.
Right. You're right. Ohio State produces about 30 or 40 welding engineers a year, and I said they only produce about 50 in the country. These other programs are, just a few engineers a year. It's mostly Ohio State. When you say graduate welding engineer in the United States, most people think of Ohio State. But there are 3 other schools, so far as that goes. Yeah. I remember, he's passed away, but Jim Cameron, who was head of welding at Electric Boat for many years, he used to describe Ohio State grads as neither fish nor fowl. Okay, but we don't have to go there, particularly since this is going to be broadcast to the American Welding Society, many of whom are going to be Ohio State grads. Anyway, if you go back historically, it turns out in 1943, in the middle of World War II, the Welding Research Council basically ran a series of articles on the universities that were doing welding research. And the first one was MIT. And if you read the whole thing, I actually posted this on the hallway across the way. But Rensselaer Polytechnic, for many years, they had a welding program. About 2 or 3 years ago, it sort of became defunct. Lehigh University has had a welding program since the 1930s, and it's still going strong under Professor DuPont. Illinois had a welding program. I haven't really seen them in welding in my career. Brooklyn Poly, I haven't seen them active in my career. Okay, but those were the schools back in 1943. In welding research in the universities today, you've got, and I put these in alphabetical order, and I also included Canadian at the bottom in alphabetical order. But there's a doubling of the schools. Brigham Young, Colorado School of Mines, Kentucky, Lehigh, Ohio State, Penn State, Portland State, Wisconsin, Alberta, Carleton, and Waterloo. Okay? So we got a lot more schools doing some welding. One of the problems, and this goes back to at Lehigh, the metallurgy was kind of where the welding was focused. Ohio State's broader. They didn't start their program until about 1948, and they actually cover more of the disciplines. But most of these, welding and metallurgy are synonymous, okay? And actually, John DuPont and John Elmer helped me compile these. Now, we also today have national laboratories, and national laboratories doing welding research include David Taylor. This is Carter Rock, okay? Used to be Annapolis and Carter Rock. In fact, the Annapolis, what they call the Annapolis detachment for many years, was actually where the welding was done. And then they decided in the base realignment and closings, they closed the Annapolis and moved it to Carter Rock. But anyway, NSRDC, that's the NAVC welding laboratory. Edison Welding Institute is the only one run by a state. The state of Ohio has basically put a bunch of money in, about $10 million a year to get it started back in the mid-'80s. Los Alamos National Lab, of course, they focus on nuclear weapons, Lawrence Livermore, competitor, but also nuclear weapons. Excellent work done at those, but a lot of it doesn't see the light of day, at least hopefully. Okay. The Naval Research Labs, that's the Office of Naval Research Welding Laboratory, or Research Laboratory. And they're not doing as much anymore, but they still have a little going on. Oak Ridge National Lab, the Department of Energy. In Sandia, there's one in Livermore and there's one in Albuquerque. They basically are part of the nuclear weapons complex. These actually, most of them still retain a mission focus. There used to be some others like Idaho National Engineering Lab, but they've sort of, over the last few years, are not doing much on welding. Okay. The ability to join a material limits the usefulness of the material. This is a slide from a place in Italy, Italy, where they talk about joining of advanced materials, okay? This is joining of glasses, okay? Joining of a foam glass material. Carbon-carbon composites to copper alloys. Here we got molybdenum to copper for particle accelerators. That's an interesting application because the first place I ran to it was in the Aegis missile system up here at Varian. They were trying to weld molybdenum to copper because they have something called the cross-field amplifier for the microwave, the phased array radar system, and they pulse an electron beam through there. Tremendous heat flux. It would melt the copper, so they put molybdenum, which has a very high melting temperature, and they had to braze the surface of it to the copper. And they had come up with this actually I could have brought some, I guess I still have some of the samples. They had developed a process originally that used an 82% gold braze alloy, kind of pricey, okay? But they came up with another one that was only 35% gold. And they said to the Navy, this one's better. We can do a 180-degree bend without it breaking, whereas the other one we could only do about a 15 or 20-degree bend and it would snap. And the Navy says, oh no, you're just trying to save money, going from 82% gold to 35%. We want the old system. They had already solved the problem. They brought me in without telling me they had solved the problem. And they said, well, we're trying to bond molybdenum to copper, and we're wondering how you would do it. And I said, well, what you really need to do is develop a transient liquid phase diffusion process. And they said, what's that? And I explained to them what it was. And it's a diffusion bonding process. It starts as a braze and ends up as a nice, perfect joint. And we discussed this, a room, about 10 engineers and me, for about 45 minutes. And then at the end they said, well, we've been able to do this. And they pointed out they'd been able to do this with 35% gold, 65% copper alloy. It had some manganese in it too, a couple percent manganese. And we've been trying to get it approved by the Navy, but they want to approve it. And so they wanted me to write a letter to the Navy explaining why it was a better process, which I was able to do and stuff. But anyway, so the Europeans are working on the same problem, but the Navy had solved this problem a long time ago, or not the Navy, but Varian for the Aegis missile system. Ceramics to stainless steels for solid oxide fuel cells, silicon carbide to silicon carbide, carbon-carbon to carbon composites. If you're going to want to build something out of these new materials, you've got to be able to join them. And in fact, in many cases, most cases, we can't get 100% joint strength. We could get 100% joint strength here because we only had to get the strength of copper. But most of these, we can't get 100% strength. They're too complex. So jointing is fundamental to our standard of living, and let me show you how things have improved. If you go to aerospace, it's enabling. We went from basically the Wright brothers to, here's a NASA, I can't remember what experimental aircraft that is, but it's a NASA experimental aircraft. In the automotive business, we went from, this is Walter Chrysler, I think. In one of his vehicles, there's a Rolls-Royce. Okay, you can look at all these appliances that we have, critical joining technology in all of them. It's important to our national security. We look at some of our national security vehicles. We've got drones. We got the X-37. Anybody seen this? Oh, some people, you're smiling. What? Is there something wrong with the X-37?
It's fake.
It's fake?
It's out of a movie.
It is? I mean,
So. Yeah, it's out of a movie. I can't remember the name of the movie. Still, that's right.
no, is it? Okay,
It's
well.
on a Navy aircraft carrier, but yeah, that's a movie prop.
Okay, well, I'll have to change that in my presentation.
I'm sure it has welds
Or joints, at least, right? Okay.
in it.
I got this actually from an email from my mother that, but it had, the Navy took pictures. Apparently you had 3 carriers on the East Coast at the same time, and they went out and did a photo shoot of 3 carriers with a B-2 bomber and I mean the task force. But I mean, I think this was a real picture of 3 carriers. Have anybody seen that? Yeah, I'll have to dig that up at some point. You don't usually get 3 carriers in the same place at the same time. Okay, you tend to disperse them a little bit more. Actually, that's another story. Since we got time, I might as well tell it. I used to spend some of the summers down at David Taylor Annapolis when they were doing the welding stuff, a part of the summer anyway. And at one time we invaded Grenada. Okay, remember Grenada? Okay, we invaded Grenada. And they had actually been waiting because there was a carrier at the Philadelphia Naval Shipyard undergoing some repairs. And they actually delayed the invasion of Grenada until that carrier was released because I think they were going to have 2 carriers on the invasion of Grenada, and they still wanted to have a 3rd carrier defending the east coast of the United States in case of, this was back in the 80s. So it turns out they started the invasion of Grenada, and about a day into what's going on in Grenada, they have a major problem with the steam system in the carrier that was left on the East Coast. And it had to go into Jacksonville for emergency repairs, leaving the East Coast of the United States without a carrier backup. And obviously people were concerned. And that's when I learned these guys at David Taylor, they were having helicopters land on their front yard at 2 a.m. to take them to Jacksonville to fix this problem. Okay? So one of the things I've learned is when the Navy needs to move, they can. Okay? Anyway. When they don't need to move, well, that's a different story. Anyway, welding's, because of security, it's important to our world standing. And I made this a few months ago, but here are some of the world leaders. It's a terrible time we're in. Anyway, joining is multidisciplinary. It involves chemistry, physics, mathematics, structural engineering, electrical engineering, mechanical engineering, materials engineering. One of the problems we face today is most people think welding is metallurgy. It's not. It's all these other things. Okay? Welding's worldwide, and it applies to everyone. And one of our goals is to make it faster, cheaper, and safer. Here's someone working on the Empire State Building a few years ago. No harness, no safety belt. And so far as I can tell, I got this one off the web. Maybe that's a safety belt, but I think probably not. I don't know. Okay. Standards for how we do things have changed over the years. So that's my presentation for the Welding Society, or the beginning presentation of why welding is important. And tomorrow I will give you a presentation on the prehistory of joining and how far back it goes. Thank you. You can cut it off.